All right, next we're going to be studying triangle points of concurrency. So if you look at the top, it says ancient Greek mathematicians knew of the existence of specific lines, which when drawn in relation to a triangle intersected in one common point inside the triangle. When the first such line was discovered, mathematicians thought that they had discovered the center of the triangle. Upon further investigation, however, it was discovered that there were other specific lines that also intersected in one common point inside the triangle, but these common points did not coincide with the previously found center point. So they had different center points of triangles. All of the discovered common points were deemed to be triangle centers in the sense that each of them could be described as the center of the triangle under certain conditions. Kind of like the idea that the mean, the median, and the mode are different averages of data, right? You could say that they're different averages depending on how you want to find the average. Is it the number that was repeated the most if you're finding the average of grades that everybody had in the class? Or is it the number that's actually in the middle of the data, or should you add them all up and divide? So all different numbers of averages or whatever. Same idea, you can have different centers depending on how you want to define things with a triangle. So when we talk about concurrency, triangle points of concurrency, a concurrency is where three or more lines intersect. And when we study these triangle points of concurrency, there are lots and lots and lots of different centers of triangles. If you look into this, there could be a whole class studying it, but we're only going to study 4 of them. Okay, so we're going to study 2 on the first day, 2 on the second day. So first, we're going to look at the centroid, which is where the medians are concurrent, where the medians. So there are 3 medians. Concurrent means all 3 medians cross at the same point. So a median connects the vertex to the opposite side and it bisects the opposite side. Okay, so it connects the vertex to the opposite side and bisects the opposite side. Okay. So if we were to draw like a little picture of that over here. So this right here is a vertex. That's a vertex. A median connects the vertex to the opposite side and it bisects the opposite side. It cuts the opposite side in half. Okay? So the centroid divides the median into a 2-to-1 ratio. The length of the portion of the median closest to the vertex is twice as long as the length of the portion of the median closest to the side that it bisects. All right, so we're going to go ahead and we're going to label that in this picture right here. Okay, so you can see that here we've got this line right here. This is a median. It starts at vertex B and it cuts into the side from A to C. It bisects it. You can see that these are 2 equal lengths right here. So if I called this would be a length of X, then this is a length of 2X. So you can see it's a 2-to-1 ratio. All right, this median right here connects vertex A to side BC. It bisects side BC. These 2 are the same length. This would be a length of Y. This would be a length of 2Y. It's a 2-to-1 ratio. This is vertex C. This is side AB. This median cuts side AB in half. It bisects it. These 2 sides are the same length. These 2 pieces are the same length. This would be a length of Z. This would be 2Z. It is a 2-to-1 ratio. All right, so the part that's closest to the vertex is always twice as long as the part that's connected to the side. And a lot of times you can tell that visually from the picture, but if you ever can't tell it visually, you can always look back at your notes and read this portion right here and then just make sense, oh yeah, the part that touches the vertex is the part that's twice as long. So you have that 2-to-1 ratio. All right, an interesting note is that Archimedes showed that the centroid of the triangle is the center of gravity. Of a triangle shape of uniform thickness and density. So if you had a metal triangle, if you had like somebody was in an art class and they cut out a triangle shape and it was metal and you had your finger and you were balancing that triangle on your finger, wherever you found that you could balance it, you have found the centroid. That is the center of gravity of that piece of the triangle. But it would have to be a uniform thickness and density. So as soon as you take that and decorate it in art class and start putting stuff on it, it's no longer the centroid. But if that was one piece of metal and it was uniform, wherever you could balance that on your finger, that would be the center of gravity. That would be the centroid of the triangle, which is kind of interesting. When working in a coordinate plane, the centroid can be found by taking the average. And when we say average here, we mean the mean. So we talked about that before, mean, median, and mode. We mean, median, and mode. We mean the average as in the mean of each of the coordinates, the x coordinates and the y coordinates. So if we have these 3 points, -4, 2, 4, 5, and 3, -1, then for the x's, we would say -4 plus 4 plus 3. So we would take all the x coordinates, add them together, and divide by 3. And so that would be, these would cancel each other out. 3 divided by 3 is 1. We would take the y coordinates, add those together. 2 plus 5 plus -1 divided by 3. So 7 minus 1 is 6. 6 divided by 3 is 2. And so that means the centroid would be at the point 1, 2. So over 1 up 2, there's the centroid right there. So you can find pretty easily if you have a triangle drawn on a coordinate grid like that, you can find the centroid pretty easily just by finding the mean of the x's and the mean of the y's. All right. So there's all the information that we have on centroid. We're going to have a lot of math problems that we can do based off this information. As you can imagine, that 2-to-1 ratio, we can do some math problems, knowing that these two pieces are equal, these two pieces are equal, these two pieces are equal. There's a lot of math problems we can do there. Obviously, having those coordinates there, we can do some math problems there. So there's a lot of math problems that we're going to be able to do based off of the centroid. All right. Next, we have the Ortho Center, which is where the altitudes are concurrent. Altitudes are perpendicular to the side and go through the vertex. I always think of the altitude as the height of the triangle. So altitude a lot of times is another word for height of the triangle. So we have a few different situations, right? You can see, so it starts, so you can see they're always drawing those 90-degree angles. So here we have the side AC, there's that 90-degree angle, so they're starting on that side, it's going straight through vertex B. Then we have side AB, there's that 90-degree angle going straight through vertex C. Side BC, there's that 90-degree angle going straight through vertex A, there's the Ortho Center. Then we have a picture like this that's a little bit less comfortable. So you have, here's this side, okay, there's a 90-degree angle, it's going straight through the vertex, so there's that altitude right here. Now on this side right here, for it to be able to go through this vertex, your altitude has to be outside the triangle because you're thinking of what's the height of the triangle. So if this triangle is kind of slanted this way, well, to see the height of the triangle, you're going to have to be the height of the triangle. If we're going this way, to be able to see the height of the triangle, oh, it was this way. I guess this is the third side to see the height of the triangle. Anyway, to go this way. So your Ortho Center ends up being outside the triangle. And so that's kind of the interesting thing about the Ortho Center, is that the Ortho Center doesn't have to be inside the triangle. Now, the interesting thing about the Ortho Center as far as our worksheet is going to go is that if you can see here, there's not number relationships between each other. There's not anything like the Pythagorean theorem. We've got 90-degree angles here, but they don't say anything about right triangles. Aside from having true-false questions about saying, oh, it's perpendicular and it goes through the vertex, and the Ortho Center doesn't have to be inside the triangle, aside from the definition and this little interesting piece of information here, there's not a lot of questions I can ask you about the Ortho Center. So when we do our questions, when we work on our practice problems for this, there's not a lot I can ask you. You basically just have to memorize these two factual pieces of information about Ortho Center, and that's about as deep as this gets. Okay, so when we practice this with our notes, we're going to do a lot of math with the centroid, and then with the Ortho Center, we're just going to know these two pieces of information, and that's about as exciting as it goes. One thing that is really interesting as well, you might highlight, is that when you have a right triangle, the Ortho Center is the vertex that's at the 90-degree angle, which is kind of interesting. And that's a piece of information that people like to point out as well. So kind of interesting there, but again, Ortho Center, there's not a lot of mathy questions I can ask you. It really is just factual information, and that's about as much as we can get. All right, the rest of the notes are going to be for tomorrow's homework.